John, sir, I'm not able to share the screen.
Now?
No. Chief from 2 minutes.
Yeah, you can start.
Okay.
No. Rather, sir, you can start.
I can start?
1 minute.
Dr. Raja will introduce you.
Okay, let's see.
So
Share the screen.
So it's my great pleasure, sir, to introduce.
No, it says I cannot share screen now.
GFAN, Dr. Raja is introducing you.
After I stop
after
sharing,
he stops, you can share the screen.
Okay.
Yeah, couple of, just a minute.
Okay, it's my great pleasure to introduce Dr. Jifang Zhu. So Dr. Jifang Zhu is working as a researcher in the Department of Chemistry, Uppsala University. So his research is generally focused on nanomaterials, which includes preparation, characterization, and performance tests. And he has been working on photocatalysts for the past 1 decade. At present, he is working on nanostructured photoanodes for photoelectrochemical hydrogen production. And as well as he is doing something like photodegradation of organic compounds. In addition to that, he is also working on electrodeposition of only semiconductors with highly photocatalytic and photoelectrochemical activity. And he is also working on synthesis and characterization of catalysts. And recently, he is also doing some work on batteries. So I'd like to welcome Dr. Jifang Zhu to deliver his talk. Jifang, you can just...
Dr. Jifang, you can start sharing your screen.
Okay. Good afternoon, everyone. So my name is Jifang Zhu. It's my great pleasure to present our work here. Thanks to the Professor Grace for the nice invitation to this excellent virtual conference, and thanks for all the audience. So today my talk is not photocatalyst. My talk is the metal oxygen battery studied by Operando XRD. So I'm working at Department of Chemistry in Uppsala University in Sweden as an associate professor researcher. And so this is the city Uppsala. It's very close to the capital of Sweden, Stockholm. It's just around 70 kilometers. And Uppsala University actually is the first university in Nordic country. It was founded 1477, and we have totally 8 Nobel laureates. So, and today my talk will cover these 4 parts: introduction and the lithium oxygen battery parts and the sodium oxygen battery part, and with a simple conclusion also. So why we are talking about the metal oxygen battery? Because as you can see from here, so half of the energy consuming is on the road transportation, and also the transportation has caused lots of environment problems. So now we are using, we call the electron vehicles, but the current technique for the lithium ion battery-based electron vehicles only can run around 400 and 500 kilometers. That's the maximum, the limitation. So, so now we need, for this purpose, so we need some new technique we call the beyond the lithium ion batteries. So metal oxygen battery, it's one category inside. So you can see the metal oxygen battery has very high energy density, which close to fuel cell, also compatible to the gas line. So this is the mechanisms for lithium oxygen battery. In the anode part, it has the lightest metal, lithium, and in the cathode part, the active component is oxygen from air. So sometimes we call lithium air battery. That's why it has so high energy density, because this is lightest and this is just air, the gas. So we have the lithium containing electrolyte between them, and also we have a cathode support. So during discharge, so the lithium will react with oxygen to form lithium superoxide, and then the superoxide will again react with lithium and electron to form lithium peroxide. So this is a two-step process. But in the decomposition, this is a one-step process. It will decompose to lithium and emit oxygen also. Yeah. So now we should keep in mind that the ideal electrochemical reaction is the lithium peroxide formation and the decomposition. Okay, so there are lots of challenges in this technique, lithium oxygen battery for the commercialization. So there has a problem with the safety, poor safety in the lithium part, because lithium is very active, and also in the electrolyte part for the decomposition, and the cathode part also. So the problem is all the components involved in lithium oxygen battery are very active, like lithium, oxygen, so on. So and also for some technical stucco for the low efficiency for lithium oxygen battery. Now we focus on these two parts. The one is side reactions, another is the efficiency. Because there's a lot of side effect reaction. So the problem is how we know that the battery is running the ideal electrochemical reactions, not for the side reactions, and how to define the efficiency, because the definition used in lithium ion battery doesn't work. I mean, for the lithium oxygen battery, because if you only judged by the electrochemical profile, you don't know those capacity it's running the ideal electrochemical reaction or side reaction. That's why the definition for the efficiency is also a problematic issue. So these two parts are connected to each other, the side reaction and the efficiency. So we need to find a powerful tool to actually to identify or distinguish the ideal electrochemical reactions. The one way the main target or topic here is XRD, because lithium peroxide has its crystal structure, so it can be even quantitatively identified by the XRD. So we start this work like 6 years ago. At that time, there were not too many groups on this Operando XRD study for lithium oxygen batteries. So the Operando XRD means the XRD measure the battery during the battery operations. So there are many examples from at that time from different groups. So here, for example, this is used normal in-house XRD. So the X-ray beam come in these slides, and this it's the sample, so on the belief and get out from another side. So this is the refraction mode. This example use Kapton as sealing, but Kapton is not good for sealing for a long time. So it can only sustain for a couple of hours. So why we need to combine the synchrotron-based power XRD? The synchrotron XRD has higher X-ray intensity, which gives better resolution. And again, it will give you the real-time resolved kinetics. So for the kinetic information study. So this is our cell. At the beginning, we use the coffee bag cell. So it's also called punch cell. This is our sample. So we have the two poles to the external circuit. We put the pouch cell. By the way, inside the pouch cell is a polymer layer, and outside is aluminum. So it has a very good sealing effect. So it can stand quite long time for several months. We put the pouch cell in the X-ray beam. So here it's a 2D detector. Then we get the diffraction ring. Then we could use the V2D program to convert it to 1D traditional XRD pattern. So then this is a photo was taken at the beam 711 in Lund, Sweden. So you see, this is the X-ray beam. So this is our battery, the cell. If we zoom in, you could see this is a battery and clamped on the X-ray beam pass. Then this as a whole, let the X-ray penetrate the battery. And this is the external circuit. This is the 2D detector. So then we actually, each one point is just one we get from one pattern. So here you get the measured or from measured lithium peroxide amount. This you get the calculated from the XRD result. Then this you can calculate it from the capacity, real capacity. This is like a theoretical curve. This is the measured data. So this is the one example for our published work for the nano-sized platinum highly dispersed on the magnesium oxide nanotube. So you could see during the charging process, the lithium peroxide peak decrease, the intensity decrease. So then we also put a silicon inside as a reference. So you could see this is the real decomposition curve. This is the theoretical curve for at the constant current density. So this is another example for this ruthenium deposit on manganese dioxide nanotube. We get the similar result. This is another example for the quinone-based organic catalyst for in the cathode for lithium oxygen battery. This is so you see this is a match with the theoretical curve. I mean, this is just depends on amount of the catalyst that you used. The important thing is you compare between the same amount of different catalysts for the effect. So this is our cathode composition. As you see, we put the conductive carbon material and the binder and our electrocatalyst, and we put also the commercial lithium peroxide at the beginning. So to mimic this battery stage, it's at the end of this charge or at the beginning of the charge. We also put 10% silicon as the reference because the silicon is chemical and electrochemically stable. and it also provides strong diffraction pattern. So we have two forms of battery. For the synchrotron Operando XRD research, we use the pouch cell because XRD can easily penetrate the whole cell because we use the transmission mode. For the pure electrochemical performance testing, we use the swage lock. The first experiment we did is to study the X-ray effect on the lithium peroxide decomposition. So this is the before charging. This is the with continuously X-ray irradiation for 3 hours. So this is without X-ray irradiation. But we can see under the continuously X-ray irradiation, so the decomposition speed almost doubled. But if we put the battery, keep it for 8 hours without X-ray radiation, without charging, which means without external circuit, then actually lithium peroxide is quite stable. It's keep the same level after 8 hours. So we also find that the acceleration of the decomposition of lithium peroxide actually is proportional to the X-ray intensity, as here you can see. But the electrochemical profile doesn't change too much. This is understandable because the X-ray only hit on the very small spot on the battery, so it's less than 1 millimeter in the diameter, so it will not change too much for the whole battery electrochemical profile. And also the accelerated decomposition is affected by the external potential, so which means the X-ray and the electrochemical circumstance both have the effect on the accelerated decomposition of lithium peroxide. So we give this purpose. So when during the X-ray irradiation, so the X-ray can kick out the electron from the lithium peroxide. So then the intermediate can release the lithium ions then for the decomposition. Without the external circuit, the electron will recombine with the intermediate back to the lithium peroxide. That's why the electrochemical condition is very important in this case. So it's not the pure X-ray damage. So as we mentioned previously, the previously battery design in the pouch cell, it's only for the charging process, because charging process, you don't need to provide oxygen. You just emit the oxygen. But if we want to study the full process with both discharge and the charge, so then we designed a new cell. So here we combine a coin cell inside the pouch cell, and on the pouch cell we have a quick connector to let the oxygen purge in, feed in this. So in the coin cell we have the hole. In the cathode part we have 9 holes, and in the cathode part we have a hole but sealed with the captain in this part. So inside the pouch cell we have the oxygen gas. So this is the battery component in the coin cell. So this is the quick connector. This is a pouch cell. So you could see that quick connector part, gas tube, and this is the pouch cell. We clamped in the X-ray beam path. This is a hole. This is a detector. This is also at 711 beam. at Max 2 in Lund. Then we also use the cell at DESE at the beam P02.1 with even harder X-ray. So this is for the first example for the new cell design, the model study, the pure fundamental research. You see that we run the lithium oxygen cell in the by using the commercial nano tube as the cathode without catalyst. So you see that during discharge, we can observe the lithium oxide formation, and during charge, we could see the decomposition, the full process. And this is the dot is we measured pattern, and the curve we use the foolproof for the refinement purpose for the curve fitting by this model structure. And what we get is, you see, this is quantitative result for lithium oxide formation and the decomposition. This is a theoretical curve, and we also get the domain size information. So this is the structure for lithium oxide. So we measured 100 and 101, these two directions, the pattern peak. So then, according to the relationship between these, so we could also deduce the information for 001, this direction. So as you can see, by the domain size change, we can divide the decomposition and the formation and the decomposition of lithium oxide by 2 stages in both cases, in discharge, the formation, also in the charge for the decomposition. And at the beginning, you could see the sharp increase of 100 direction. So we know it will get a 2D structure at the beginning, but then it will decrease, which means then at the stage 2, it will form at the edge of the disk for the small crystals. So that's why you have the domain size decrease, because the domain size is the average for all the crystals. And the same for the decomposition. The first day increase is because the small crystallites will decompose firstly, but then followed by a sharp decreasing. So this was confirmed by the SEM observation at different stage. So, for example, at the very beginning, we see the disk, but then we see the toroid structure, but then the toroid become disk again and decompose. So this is the SEM observation. And also, we use the new design cell for the new catalyst research for titanium carbide used in the lithium oxygen battery. This is for the discharge stage. This is for the charge stage. So the brief summary or conclusion for this lithium oxygen battery is it can track the evolution of lithium oxygen battery. This is a 2-step process, both for discharge and for charge. So this technique could be extended to lithium oxygen, sodium oxygen battery. The sodium oxygen battery, has its advantage in the price, the abundance of the metal. So it has lower energy density compared to lithium oxygen battery, but small overpotential, and it's cheaper. It has most of the problem as lithium oxygen battery, but it has, in addition to that, it has 2 other problems. It has even poor stability than lithium oxygen battery, and also it has several discharge products. So we use the same cell for the sodium oxygen battery. The first work is we compare two different electrolyte. The one is NaPF6, another is NaOTF. So you could see that in both cases, for the discharge has the high efficiency, but for NaOTF it has higher capacity, and by compare the domain size in the NaPF6, it just increased continuously, but for NaOTF, it increased at beginning, then decrease. The reason for that is for the NaPF6, we could see several big blocks, big size of sodium superoxide, but for NaOTF, it has the even size distribute. So we give the purpose for the growth of sodium superoxide because NaOTF has higher solvability of the sodium superoxide, so it can form in the solution until the situation, until the saturated, so it can start slowly precipitate. So you get this. But since sodium superoxide has the very low solubility in the NaPF6, so it prefer growth on the existing sodium superoxide. That's why you see the big blocks. So this is another example for the stability research of sodium superoxide in the sodium oxygen battery. So we found after discharge of sodium superoxide battery, so it self-decomposed. Then we listed the reason for the possible reason for this self-decomposition, and we could see that the self-decomposition is quite fast actually in this. And if we remove the sodium metal, we could see even after 80 days, we still see sodium superoxide, but with the existing of sodium, so we could see nothing actually. So that's the main reason for the decomposition. Also, the solvent has the effect, and also the self disproportionation has the effect. And we found some the sodium superoxide hydrate and unknown phase is connected to the oxygen feeding because the trace of amount of water that we found. So this is the by the XRD measurement, quantitative analysis, we get the main problem is for the sodium part because the sodium superoxide dissolved in the solution, but then continuously react with the sodium, so make this fast decomposition. Okay, I should thanks for all my colleagues in those works, and thanks for the funding support. Thank you for your attention.
Thank you, Jifang, for your nice talk. We have got some questions for you.
Yeah.
So, what about the discharge stability of Li2O2 anode batteries over LiCOO2 batteries?
Sorry, what about the
discharge stability?
Yes.
Of Li2O2 lithium iodide anode batteries over lithium cobalt oxide batteries.
I try to get back to what about the stability for the discharge for the
discharge stability of Li2O2 anode batteries over LiCOO2 batteries. Lithium air anode battery and lithium cobalt air battery.
for lithium oxygen battery and the lithium
Yes, yes.
between lithium oxygen battery and lithium ion battery.
Yeah, yeah.
But lithium oxygen battery is much more unstable.
Okay.
Compared to the lithium ion battery, it's much more stable. But compare discharge process and the charge process even more unstable, more unstable, let's say. Yeah. Because the charge process, you have higher voltage. It will decompose electrolyte if it's higher than 4.5, for example. Yeah.
Another question is when you just use metal air battery, so what is the most important parameter that you consider? Because there are a lot of choices such as lithium, sodium, zinc, oxygen batteries. So
stability is the most important. Stability, which means you can run many cycles. I mean, this when we're talking about the many cycles with quality, which means with higher efficiency. So the ideal electrochemical reaction should make the main contribution, not the side reaction. So the quality for each cycle is very important.
whether these oxygen batteries have long life than other batteries?
Good question. I mean, when you're talking about the long life, I would say no, because if you judge by the cycle number, it is not far lower than lithium ion battery. But if you judge the time, because normally when we cycle this metal oxygen battery with the very low current density, so one cycle we always use more than 30 hours. In that case, you could see long. But if you judge by the cycle number, no, it's generally we think it's short life.
And the last question, whether this Operando XRD can be used only for battery electrode material, or can it be extended to another kind of materials as well?
For which technique? You mean XRD?
Yeah, XRD, Operando XRD.
Of course, it could be used other techniques. I mean, but as you can see that the device design or the setup architecture is actually very important. It's related to engineering. So if you have good design, so you can utilize this technique.
Okay. Okay, Jifang, thank you very much for your time, and thank you for joining.
Thank you.
Thank you, Jifang, again for giving a nice, interesting talk.
Thank you. Should I quit?
Yes.
Yes, Dr.